Okay, you can see that you're staying there. Okay. Got a few more people joining. We'll start in just a minute. Okay. Anyone else waiting to join? All right, we will go ahead and begin. First of all, can everyone hear me?
Yeah.
Okay, great.
You're a little quiet, but I can make it out.
All right, I'll try to speak up. Okay, we have Emily Goodrow with us, who's going to make a quick announcement.
Yeah, so like you said, I'm Emily. Most of you know me. I'm just here to announce that ACES is still open. A lot of you have come to tutoring or like you tutor yourself. But I tutor organic chemistry, and so does Gabby Crow. And you can do walk-in sessions, which you just join like a link, and then we're just sitting there, and you can just, it's all virtual. Or you can make a face-to-face appointment. And all that, you should have access on your Canvas to ACES, and you can find all that information on there, but we encourage you guys to come to tutoring. So hope to see you guys there. Thank you.
Thank you. Okay, so I'm going to share my screen here after I open up a file. Okay. All right, so I'm going to summarize some of the main points from this chapter. Okay, we'll then wrap it up, and then I'm going to talk about biological differences between enantiomers. Chirality means handedness. Achirality means not handed. That is, you can't tell the difference between the original object and its mirror image. They're identical. Enantiomers are non-superimposable mirror images.
Wait, Dr. Trump, sorry to disturb you, but Khalid said that he's waiting. Could you let him in?
Okay, I'm not seeing him here. Oh yeah, there he is. There he is.
Okay.
Okay, got it. Yeah, I didn't see him on the screen, but there he is. Okay, he should be joining in just a minute. Okay. Right, so chirality means handedness. If something is achiral, it doesn't have this property of handedness. Enantiomers are non-superimposable mirror images. You have to include the word non-superimposable. Okay, everything has a mirror image except a vampire, and it's a matter of whether the mirror image is superimposable or not. Okay, so usually when I tell a chemistry joke, there's no reaction. Enantiomers belong to a class of compounds called stereoisomers. And we can usually identify asymmetry, which is the underlying cause of chirality, by looking to see if a carbon has 4 different groups or atoms attached to it. And such a carbon is referred to as an asymmetric carbon, or a chiral center, or a stereocenter. Okay, they all mean the same thing. Okay, other elements besides carbon can have chirality, such as the nitrogen that's shown here. All right, a plane of symmetry will negate chirality. Okay, if half the molecule is a reflection of the other half, and in this case we have 2 groups that are the same, so I only have 3 different groups rather than 4. Here's another example of a plane of symmetry where we have a cis cyclic compound. Okay, so this cannot be chiral. The trans isomer, though, can and is. Okay, these are non-superimposable mirror images. We talked about how to determine R and S configuration. We identify the 4 groups, and then we prioritize based on the first atom that's connected, based on atomic number. In the case of a tie, okay, here we have carbon and carbon, we go out to the next one. Okay, so the next one out for CH3 would be hydrogen, and here we have oxygen. So the carboxylic acid takes priority over the methyl group. Nitrogen takes priority over carbon. Since nitrogen is atomic number 7 and carbon is atomic number 6. Okay, so here is a listing of some examples of relative priorities based on atomic numbers. We can have chirality if we have isotope labeled atoms, such as carbon-13. If we have a carbon-13 versus a carbon-12 methyl, the carbon-13 takes priority. That's based on atomic mass. Okay, so we assign priorities. The lowest priority group has to be away from you. And then we look at the orientation of the other 3 groups that are coming toward you. If they're in a clockwise arrangement, then it is R. If it's counterclockwise, then it's S. In this example, this would be S because it goes 1, 2, 3, that's counterclockwise. Okay, I'll mention this again. If there's a tie, we go out to the next atom. And 1 bromine beats out 2 chlorines. Okay, bromine has a higher atomic number than chlorine. As soon as we find a difference, then we stop. Double bonds, we count that as though it were bonded to 2 of the other atoms in question. A carbon-carbon double bond, we count that as though it were bonded to 2 carbons. A CO double bond, we would count that as as though it were bonded to two oxygens. Okay, I'm moving through this quickly. This is what we've covered, and I'm just reviewing. Okay, so here's a cyclic compound, and again, hydrogen is last, and this is set up as it should be, where hydrogen is away from us. Okay, so we've got carbon, carbon, carbon. This carbon that's bonded to three carbons, or three bonds to carbon, takes priority over these CH2s. So this is first priority. These are the same, so we compare this one and this one. And the oxygen wins out, so this side is number 2, this side is number 3. Okay, so this is the S. Okay, enantiomers have very similar properties. Many properties actually are exactly the same. But mixtures of enantiomers may actually have different melting and boiling points. Optical rotation is a physical measurement that we make. Okay, something that is achiral is not optically active. We don't measure any rotation. Two enantiomers with the same concentration would rotate light in the same number of degrees, but in opposite directions. Okay, this is a crude diagram of a polarimeter. The sample cell is here. The sample is either in solution or it may be a pure liquid, but usually it's in solution. Okay, this is an important point. There's no simple relationship between plus and minus in R and S. Okay, if we observe that a particular compound has a clockwise rotation of light, okay, we can't predict whether it's R or S. Okay. If we know that it's R and we measure the rotation to be clockwise, then we can predict that the S would be minus. Okay, but there's no simple relation. We're talking about two different things. I'm going to skip over this. Okay, I have several more examples of biological discrimination, which I'm going to talk about. Okay, here's another definition, racemic mixture. Okay, this is where you have exactly the same amounts of two enantiomers, 50-50. And in a polarimeter, a racemic mixture will not produce an observed rotation. Okay, so we say that is achiral. Optical purity or enantiomeric excess. Okay, we use this formula. It's the observed rotation over the rotation of the pure enantiomer. If we have a racemic mixture, then the optical purity or enantiomeric excess would be 0. Okay, the key word here is excess. Okay, so if you have a non-zero optical purity or enantiomeric excess, that tells you you have an excess of one over the other. Okay, so you don't have you have something other than a 50-50 mixture. Okay. If conformers are mobile, then the chirality depends on the most symmetric conformation. Okay, we talked about non-mobile conformers. Okay, in this case, there's asymmetry about a line rather than a point. This compound and this compound here are, in fact, non-superimposable. Same way with these two allenes. Okay, Fisher projections. This is a two-dimensional representation of a three-dimensional shape. Vertical groups are back, horizontal groups are forward. Okay, and because we draw the carbon skeleton vertically, oftentimes hydrogen is forward rather than back. Okay, so if we were doing the configuration here, we've got carbon, oxygen, carbon, and hydrogen. Hydrogen's last. Oxygen would be first. Okay, carbon with an oxygen would be second, and then methyl is third. Okay, so this would go 1, 2, 3, like that. 1, 2, 3. Okay, that looks counterclockwise, but you're looking at it backwards. So it's actually clockwise. So that's R. Sometimes the question comes up, will the Fisher projection always be backwards? Not always. You always have to check, but usually it is. Okay, there are some Fisher formulas that you can make where the arrangement is actually correct. Okay, but usually it's backwards. Okay, this is, I think this is good to review. The highest oxidized carbon is at the top. Okay, so in this example, the highest oxidized carbon would be the CH2OH. In this example, it's the carboxylic acid. That's the most oxidized. So we put that up at the top. We can rotate 180 degrees in the plane, and that doesn't change anything. But we can't rotate 90 degrees for fission. Okay, one thing about Fisher projections is it's very easy to draw the mirror image. All right, so for this compound, to get the enantiomer, we would invert both of those chiral centers. Let me zoom in just a little bit here. Okay, so to make the enantiomer, we invert both of the chiral centers. So this is the mirror plane. This is a reflection of the original molecule. Okay, and it turns out that these are both S. Cis-trans isomers are considered to be diastereomers. Definition of diastereomers, they are stereoisomers, but they're not mirror images. Okay, in this example, the trans 1,2-dimethyl forms are enantiomers. Okay, they're non-superimposable. The cis and the trans are related as diastereomers. Okay, this and this are not mirror images. Okay, well, it turns out that it just so happens that the cis has a plane of symmetry, and it is achiral. Okay, but the trans does not have a plane of symmetry. Okay, so here we have 2-bromo-3-chlorobutane. And to go from the original compound to its mirror image, we switch both of these. And if we switch one but not the other, okay, this is SR, over here this is SS, these are now diastereomers. Okay, stereoisomers that are not mirror images. All right, so when compounds have two or more chiral centers, then they have enantiomers, diastereomers, or mesoisomers. Okay, let's go back just a minute here. These are diastereomers, and each one of these has a mirror image, which is non-superimposable. Okay, but back here, the cis is a diastereomer, but it's achiral. So that's a meso. Okay, definition of a meso, it's an achiral diastereomer. A lot of times I'll hear a meso compound something with a plane of symmetry. No, it's more than that. The usual reason it's a plane of symmetry, but it has to have chiral centers and it has to have diastereomers to be a meso. Okay, so if you have one chiral center or one stereocenter, that molecule is going to be chiral. Okay, it'll have two enantiomers. If you have two chiral centers, okay, it may or may not be chiral. Okay, so enantiomers have the opposite configurations at every corresponding chiral carbon. Diastereomers have some matching and some opposite configurations. Meso compounds have internal mirror planes. They also have stereocenters and they also have diastereomers. Okay, so this is the maximum number of isomers that are possible. If you have one stereocenter, there are two possible stereoisomers, two enantiomers. If you have two stereocenters, then 2 to the second power, or 4, stereoisomers are possible. In this example right here, if I switch one but not the other, turns out that this diastereomer is in fact a meso. Okay, so in this case, we have fewer than 4. We only have 3 stereoisomers because one of them has a plane of symmetry. So 4 is the maximum. And each time you add a stereocenter, you double the number of possible stereoisomers. Cholesterol, the molecule cholesterol, which has 4 rings, it actually has 256 possible stereoisomers, but only one is the one we see in nature. Okay, so these are enantiomers, 2R, 3R. We invert both of these, 2S, 3S. This one, the second and third, the first and the third, first and the fourth are related as diastereomers. We invert some, but not all of the chiral centers. Okay, and then these are enantiomers of each other. Okay, meso compounds possess achirality because of the plane of symmetry. Okay, absolute configuration. That means that we know exactly how the atoms are arranged in three-dimensional space. Relative configuration is an experimentally determined relationship between the configuration of two molecules, even though we may not know the absolute configuration of either. Okay, so an example of relative configuration, if we did a polarimetry measurement and we determined that we had two enantiomers, that they had opposite rotations, but we didn't know which one was R, which one was S. Okay, so that's an example of relative configuration. Okay, absolute configuration, we would know. All right, so this is basically the same example that I have on the board, except with bromines instead of chlorines. Okay. Enantiomers have the same melting point, same boiling point, same refractive index. Diastereomers, though, will have different physical properties. Okay, because enantiomers have the same boiling point, it would be impossible to separate enantiomers, say, by distillation. Okay, to separate by distillation, they have to have different boiling points. Diastereomers, though, can be separated. Okay, because diastereomers belong to the same class of compounds, they often have properties that are very similar. Enantiomers are difficult to separate. Okay, and I'll mention some of the ways that we can separate enantiomers. Okay, one way is to convert enantiomers into diastereomers and then separate them. Okay, and this shows that enantiomers have the same physical properties, but diastereomers have different properties. Okay, so here we have cis and trans 2-butene, butene. They've got different boiling points, 0.9 and 3.7. Here is plus and minus 2,3-dibromosuccinic acid. Both of them have the same melting point, but the meso has a much higher melting point. Okay, and main reason, because of the high symmetry, it would pack more efficiently in the solid. So it would be more difficult to melt. Okay, the very first separation of enantiomers was done in 1848 by Louis Pasteur. Louis Pasteur lived in France. The French government was very interested in the chemistry of wine, and they supported a lot of his work. And one particular compound that occurs in wine is tartaric acid. And there are actually three isomers. There's a plus and minus, the two enantiomers. There's three stereoisomers, sorry. There's the enantiomeric pair, and then there's a meso, tartaric acid. Okay, so we took a microscope and a pair of tweezers and physically separated the two enantiomers because the crystals were actually mirror images of each other. Okay, there are enzymatic methods that can separate enantiomers. Okay, one enantiomer will bind to an enzyme and the other one will not, or it will bind better than the other. And there's some applications where this can be done. Okay, this is an example of conversion to diastereomers. Okay, so we have R and S butan-2-ol. Okay, this is butan-2-ol. And then tartaric acid. Like this. So this is RR tartaric acid. And if you take a carboxylic acid and an alcohol, okay, you can make an ester. Okay, and that's what this is showing. Okay, so we have this racemic mixture, and then we add just one enantiomer of the tartaric acid. And that will produce two esters, which are diastereomers. This is RRR and this is SRR. Okay, so we've inverted one center, but not the others. Okay, and these then can be separated because they are diastereomers. Okay, and that's what this is what this is showing. And then once we separate them, we can actually cleave the esters back to the original alcohols using dilute acid. Okay, column chromatography. This is what you're doing in lab tomorrow. It is possible to separate enantiomers using chromatography. You have to use a special stationary phase, one that actually has chiral groups bonded to the silica gel or the alumina, the solid phase, that will bind one enantiomer more tightly than the other. I had a research project once that produced a racemic mixture, and I wanted to separate them. I looked at chromatographic separation, but these chiral columns are really, really expensive. So it's better if you can separate the enantiomers another way. Okay, if you're manufacturing something, okay, like a pharmaceutical, okay, and if one enantiomer is biologically active and the other is not, or the other one's harmful, then you don't want to produce a racemic mixture because you're gonna throw away half your product. Okay, so you want to develop methods that will produce the desired enantiomer either exclusively or preferentially. And there's a number of ways to do that. One of them involves including the use of a chiral catalyst. And this was such a big deal that it was the basis for the 2003 Nobel Prize in Chemistry. It was awarded to Barry Sharpless at Scripps Institute in San Diego and two others. They did a lot of work on enantioselective synthesis and various methods. So they were awarded the Nobel Prize for that. Okay, I have about 10 minutes remaining. I think that we can at least get started on the next topic here. Let me go to Canvas. Okay, I've uploaded a couple of files here. Wait for Word to open. Okay. In the June 1996 issue of the Journal of Chemical Education, I realize that's quite old, but a lot of the examples are still very relevant today. Okay, notice the cover art there. And the title of this is When Drug Molecules Look in the Mirror. Okay, there's a number of possibilities between drug enantiomers. They can have the same activity. One can be active, the other one does nothing. One can be beneficial, the other one can be harmful. They can have different potencies. Okay, they can do the same thing, but one is more potent than the other. There are also some instances where both enantiomers are beneficial, but they do different things. They respond to different enzymes, for example. Okay, so when drug molecules look in the mirror. Okay, some of the biological differences include different odors. The compound up at the top is called limonene. And chiral center is where this isopropenyl group meets the cyclohexene ring. Okay, right here there's a hydrogen. Okay, your olfactory receptors are chiral, and they recognize molecules based on their shape. Okay, so for limonene, one enantiomer smells like oranges, the other one smells like lemons. Right, carvone is another example here. Again, this is the chiral center. Right here, there's a hydrogen. Both enantiomers of carbone, like limonene, occur in nature, but they have different odors. Okay, one smells like spearmint. The other one smells like caraway. If you're not familiar with caraway, they use it in rye bread. If you know what rye bread smells like, a lot of that comes from caraway. There's also some other spices. Okay, they can have different tastes. This is aspartame, artificial sweetener, also known as NutraSweet. And one enantiomer tastes sweet, the other one tastes bitter. Okay, so your taste receptors are actually chiral as well. Okay, I'm going to come back to thalidomide. Okay, here are a couple of examples of some drugs that are marketed both as the single enantiomer and as the racemic. Some of you might be familiar with Nexium or omeprazole, Prilosec. It's used to treat acid reflux. Nexium is just the single enantiomer, whereas Prilosec is the racemic mixture. Okay, where's the chiral atom on Nexium? Okay, it turns out it's not a carbon. It's a sulfur, yeah. Okay, a lone pair can contribute to the chirality. A lone pair of electrons is actually below hydrogen on the priority scale. Okay, and then another example here is Lexapro and Celexa. Okay, these are used to treat depression. Celexa is the racemic, and then Lexapro is a single enantiomer. Okay, so Lexapro is more potent. The chiral center is right here. If I can find my cursor. Okay, it's where the benzene ring meets this five. Here we go. Okay, this is the chiral center right here. 4 different groups. Okay, and then let's see, I have a couple minutes remaining. Let me go back to thalidomide. Okay, thalidomide, okay, has a chiral center right here, where the nitrogen meets a 6-membered ring. Thalidomide was invented in Germany in the 1950s. It was they started using it in 1953. It was a sedative, analgesic. It was given to anti-nausea. It was given to pregnant women to treat morning sickness. And they started realizing that it was causing birth defects. So there were about 2,000 babies that died and about 10,000 that had birth defects. And the company tried to introduce it into the United States. But there was a Canadian-born doctor that worked for the Food and Drug Administration. Her name was Dr. Frances Kelsey. and she was reviewing it, and something didn't seem right, and so she blocked the approval of thalidomide in the United States, and as a result, there were only 17 babies that were affected in the United States. And it turned out she was right. She was honored by President Kennedy with the highest civilian honor. She died a few years ago at the age of 101. But anyway, the way that this relates to chirality is that the thalidomide that was being produced was a racemic mixture, and one enantiomer was beneficial, the other one was causing the birth defects. And there's a twist on this story, and that is there was a physician in France that was treating patients with leprosy, and they were miserable. It seemed like he couldn't do anything to help them. And there was some thalidomide left over on the shelf, and they happened to be all male patients. And he thought, well, maybe this could ease their suffering. And to his surprise, within a very short time, their leprosy sores started healing. And so today, this can be used to treat or prevent leprosy. It also can be used to treat a form of cancer called multiple myeloma, because it inhibits the formation of new blood vessels. Okay, and there's a book that was written about thalidomide. It was called Dark Remedy, which is it's a very interesting story. Okay, so that's all for today. Okay, so I'll see you tomorrow in lab. You should have all received the instructions. Is that right? Yeah, good.